What's up, guys? We're back at it. What's today? Friday, lesson 5.3 part 2. Let's go, Kushow!
Queso did it better.
Queso did it better. Queso would eat. That's what it
Why is it queso? Do we know?
Yes.
Did it have something to do with like cheese?
No.
No.
Sure.
We'll take that.
Anyway,
Queso
I can show you some on
anywho, I don't think I want to know anymore. Okay, so yesterday we watched a little video and none of you guys, like most of you guys didn't pay attention to it, which was a whole thing, and I went into my whole speech about how like your cell phones are like rotting your brains and stuff.
Oh, I hardly use my
Awesome.
phone.
Good. That's not good.
I'm not even allowed to have like any of the stuff that like goes on your brain.
Yeah, I actually make sure they get good sleep so they can pay attention.
That's so early. I pay attention in school and I go to bed at like.
They're
You said they go to
little.
bed at 8?
I go to bed at like.
They're little.
Oh
I go to
yeah.
bed at 8.
My girls go to bed at like 8 and 9.
Oh.
I go to bed at 9.
Okay. All right, so pay attention, take notes. We're continuing with exponential functions. So yesterday we watched that little video where the guy talked about exponential functions. He compared the function on a graph with a linear equation on a graph that had similar numbers, but a linear equation and a function and an exponential equation are so totally different, so they're going to look very, very different on a graph. So yesterday we saw how the linear function was a straight line. What? I didn't mean to. Okay, yesterday we saw that the linear function was a straight line. This better be important.
The linear was additive and the exponential was multiplied.
I did pay attention the second time.
The second time when I got mad, right?
Yeah.
You guys respond to that better. You like getting yelled at. Okay, so yes, multiplicative. The linear function was additive. It was that constant change by addition, just like the x moves over 1, the y goes up 2. The x moves over 1, the y goes up 2, adding 2 every time. The exponential, instead of going on that straight slope, that line was going whoosh, like that and shooting up so quickly. As x increases, y increases faster and faster and faster and faster, at least in this type of function. We'll see some decreasing and things like that in another, we'll see that today actually. Okay, so again, we have this exact same function that we used yesterday, a very basic, the function of x equals 2 to the x power, where x is our exponent, and that is our domain, right? And then f of x is our output, our y values, our range. There are so many names for these things now. So with this example, we already worked out all of the, how did we get 1/4 from -2? Well, we plugged in, we did this yesterday, right? On the table? We actually plugged in, we did 2 to the -2 power, right? And then got 1 over 2 squared and then got 1 over 4. We did that. Did we also talk about the constant ratio?
No.
Yes.
Okay.
Yes, we did.
Yeah, you did.
What was the constant ratio? Yes, the number that the x value is being multiplied to get to the next y. Did I say x or y? It's y. I don't know what I said, but it's y. The number that the y value is being multiplied by to get to the next y value. So, and I think we did this yesterday, but I'm just going to ignore my fractions just for a second because it's so much easier to spot it with your whole numbers. What is 1 multiplied by to get to 2?
2,
What is 2 multiplied by to get to 4?
2,
And what is 4 multiplied by to get to 8?
2.
Good, we see the constant ratio is 2, and we can also, I think we did this yesterday also, we can prove that to get from 1/4 to 1/2, you actually can multiply times 2 as well, right? And again, 1/2 times 2 is 1, so the constant ratio here is 2.
It actually makes a lot of sense.
Yeah,
Makes no sense.
Oh,
Makes more sense.
tell me what doesn't make sense about it. I'm just curious. Does it not make sense?
It's still a lot.
It is a lot. I will definitely give you that. I'm just not sure how it doesn't make sense.
You're just multiplying 2, so if you have 1 times 2, what's that?
Let's break down the words constant ratio, okay? Constant ratio. I want to just be careful of like, if something doesn't make sense, we need to go back and check to make sure it's correct, because if it doesn't make sense, then it's wrong. But if it's that we need more time to process it, let's like acknowledge that, because we can kind of go back and break it down a little bit to process it. But I just want to be careful of like using the vocabulary like this doesn't make sense, because then you're like telling your brain that like you're not going to understand it, rather than like I haven't processed this yet, which is like the information is there, I just need to break it down a little bit more and take some time, and then it's more of like a positive attitude. Yeah.
when like,
Basically, you need to go to the basement for a little while. I'm just kidding. You're like a negative excellent. It's just a joke.
when like seeing it like on a homework, we would like take the equation and then put it on the graph, or
Oh, I see what you're saying. Like,
Yeah.
what will the homework questions be like? They will be going both ways. Like, and we'll see that in the examples. You can be given an equation or a function, and then they'll say graph it. Or they'll give you a graph and say, what is the equation? So today, our examples are going to be showing you how to write an equation when you're given a function on a graph or a table of values, and how to graph something if you're given the function. Right now, we're just really identifying all of the little parts, so we understand all of like the characters in the play before we're like, so how does it end, you know? Okay, so let's talk about constant ratio for a second. What does constant mean?
always.
Same.
So same. And then ratio means fraction, which I know that's confusing because you're like, but 2 isn't a fraction. It isn't?
Boom!
I'm like a magician.
Dude.
I'm the magician.
Isn't it a function of
Get it? Mathematician? Mathematician? Thank you. Anyway.
Genius.
Anyway, we will have constant ratios. You will see, we will have constant ratios in future functions where the constant ratio is actually a fraction, like 1/2 or 1/3. Go ahead.
It's like pause.
Oh.
So that's why we call it a constant ratio, because we can't say it's a constant whole number, because sometimes it's a whole number and sometimes it will actually be a fraction. So we're just going to call them all ratios, because sometimes they'll be fractions and sometimes they'll be whole numbers that also can be written as ratios. So we'll just call it a constant ratio. Now, just to say it again, don't worry about these values for now, not because they don't matter, but because they're a little more confusing than working with numbers that we know and love. How are these x values increasing?
By 1.
By 1. To get to each next point on the graph, the x values are increasing.
Multiplied, not added. No, on the x.
You multiply
The
the y.
x values. So the x values, x.
Yeah.
We were just doing the y values when we were multiplying.
Okay.
They're totally different. X is your input, Y is your output. We have to recognize that they're so totally different. Now, your input is increasing by 1. Now, you can increase it by, like, I don't know, you could put like a 0.5 here and increase it by 1/2, but why would you want to plot that, right? Just increase them by 1, and then, once you realize that the x's are increasing by 1, then you can find your constant ratio to see what number your y value is being multiplied by to get to the next y value. 1 times what is 2? Good. And then you just check it again. 2 times what is 4? Good. 4 times what is 8? Good. So you see the same ratio or fraction, 2/1, is being multiplied over and over and over. The fact that it's multiplication is the very thing that makes this an exponential function. If this were plus 2 plus 2 plus 2, if this said like if this was 1, 3, 5, it would be linear. So this is the very thing that makes it exponential. Now, this constant ratio just happens to be the base. And I think Jacob asked me yesterday, he said, will that always be the case? Where your constant, didn't you ask me yesterday?
Yeah.
Then you said, because when we were doing 5 to the x power, you're like, will that also be? And I said, yes, because this constant ratio is the base of your exponent. And we're gonna identify that much more clearly in the upcoming examples. Are we better than we were before in terms of breaking it down, Brianna? Yeah, I think we've worked with linear equations so much that it is very hard to jump from that to exponential. That's why I did that video yesterday, because this lesson, this is literally example 1, and it makes no reference to linear equations. It's almost like we just forgot about them, and I don't want to forget about linear equations because they were part of my life for a while, and I just feel like they're kind of important to me, and I really...
You wanna have...
Do you think my sadness is funny? Let's
Yes,
have
he
a moment.
Her voice is just like.
I just don't like to just like abandon linear equations that quickly, okay? I need to see like, well, what did we learn from linear equations? How are they different?
She wants to be your therapist.
Yeah, that's all.
I said therapist.
Yes.
Your sadness brings me happiness.
Oh.
Yeah.
I'm glad you guys are just a bunch of sickos. Okay. Now that we have kind of analyzed some things about this graph, we're going to talk about its...
Great observation.
We're going to talk about its key features. What do they mean by key? Important. Main. Very good. Those are the two synonyms we thought of earlier. Are there any other synonyms? Synonym. So we're going to talk about the main features of this function. We're going to talk about the important features of this function. For example, let me see. Now the first thing that they say, which I'll just go through this kind of quickly. Remember the word continuous that we used? Do you remember the word that was not continuous? Starts with a D.
Determine?
Okay, we looked at, there were, you're not. Remember when we had graphs
Describe.
of linear functions and some were continuous and some were,
Divided?
yes, you got it. What is it?
Distributed?
Discrete.
Discrete.
How about just re-rock and
Louis said it first.
You want to
First one.
Oh, I wanna go first.
Not
Who won?
Bobo.
I never said I was going to give anybody candy.
Yay.
Oh my god! That's a wild.
Now you guys see why I need to eat a lot of ice cream, okay? That's my therapy. You want to talk about therapy? Ice cream therapy. Are you guys okay? Don't choke on your John Manches. Can we keep going? Yes. We had continuous and discrete, right? Where there were like empty spots in between the points. So one of the key features of this function is that it is continuous. We are connecting the dots, okay? Because technically, if we're given this function, I can make up any x value I want for it. I could make an x value of like 1.5 or 0.32 or something like that. And I could get a y value. So it will be a continuous function. It also mentions that it's continuous even beyond the x values that we can see, which basically just means the arrows are going in both directions and it continues beyond what is actually visible here. Okay?
Pardon me.
Yeah.
Another key feature is the domain. What does domain mean?
Like an area.
X. Very good.
2. I'll remember.
Okay.
I will remember.
Okay. The domain is our x value, right? Our x values. The x values are the domain. What is the domain of this graph? X.
Oh wait. It's 2. It's 2. It's a number. It's 0. It's a number.
4.
It's 6. It's 3. It's 1. It's 1. It's negative 4.
Wait a second.
What's the question?
What is the domain of this function?
What is the y? Yes, the y. No, are you? The domain is y or x?
X.
X. So would it? Would it be 8? No, that's y. One's the
Queso.
queso.
What's the
It's
domain?
2 to the x.
No, I know.
Wait.
Oh wait, I know.
All real numbers.
You got it, girl.
What was it?
What was it? All real numbers.
I said every number. I said those are all real.
You also said like 18 other answers?
But
Okay.
they're all real numbers.
Okay.
Shut up.
Can I move on, please? The domain is all real numbers because we could literally put any x value in and get an output, right? So this graph continues all the way to the left on the x-axis and all the way to the right on the x-axis. And even though it's shooting up really high and really fast, it's still moving over as well. It's just gonna shoot up way faster than it is moving over, but it still moves over. So it is all real numbers. And you can write that as x, the domain is x is a real number, or you could simply say x is all real numbers. Both of them are correct. What about the range? Lex, I'll give you another shot.
Oh, no, it is. The
Don't
range.
choke.
Yeah. The range. I was like trying to remember. Is it
Well-
1? Oh my god. 0?
Jocelyn, oh. I was really hoping you were raising your hand to answer the question.
Queso.
No?
You should call on queso.
Can you try?
You should call on
Don't
queso.
tell her, Faith. Yeah, y is correct. So how can we describe the range saying using y? Meaning what numbers qualify as the range? What y values are included? Grayson. What?
All real numbers.
No.
I got that.
You're right.
Y is greater than 0. Earlier.
Say it loud and proud.
Y is greater than 0.
Y is greater than 0. That is the range.
Oh yeah.
I get at least one.
I'm gonna play a very fast.
Good. Y be greater than 0, and if you use the key word, you will be my best friend.
What's your best friend?
Queso.
Oh, because like when it's like when you
Yes, Queso.
so like the x the like x line when it's
Can you use the like really
so
special
on the
words?
x-axis when it's going down, it like never touches 0, so it has to be greater than 0.
Very good.
You're not this.
I know the word though. I know the word though.
Here's your plate. Here for the camera.
Miss Lizzo, I know the word.
What's the word?
The word, I wrote it down. It's asymptote.
Very good. What's an asymptote, Lex?
It's the line that the function is trying to reach but never does.
Very good.
I got that defect. Oh, actually,
Yes,
what
and
am I
when you come back, try to answer a question, okay?
Actually, it's watermelon.
Sorry.
Don't just say you have to death. What? Are you okay?
You good?
My ears wrong.
Oh my gosh. You're not deaf. Don't do it, Grayson. Stop. What? Okay, so we said the range is y is greater than 0. The asymptote is, oh, now somebody tell me what the asymptote is on this. Not the definition of an asymptote, but what is the asymptote? Faith.
Is this the thing where like on the side is the
No, I need you to actually tell me like what the asymptote is.
I'm having a stroke.
On this graph. I don't think, Brianna.
Negative infinity.
No. No.
Y
No.
I did the whole thing.
You were kind of on the right track, but the asymptote is, Lily, could you pay attention, please? Giving out a lot of information. No, if you don't like it, give it to somebody else, okay?
Oh,
I'll take it.
After class. After
I'll be your
class.
best friend.
Or maybe at the end of class, I'll let you trade that.
Oh, good job.
Yeah, that's if I said
Sorry, you know, yo, what?
the exponential. If I said the exponential. If I said the exponential line, would that be right?
No,
Why not?
because that doesn't make any sense, like Brianna said. And that legit doesn't make sense. No. The asymptote has to be a specific equation of a line. If you told me that the asymptote is the x-axis, I would have also said that is correct. But we also like to write it as an equation of a line. Technically, the equation of the line for the x-axis is y equals 0. Okay, we're gonna move on with our lives.
But it doesn't touch 0.
Oh, what the flip?
Exactly, that's why it's the asymptote.
So you're having a stroke.
Y equals 0.
The asymptote is the x-axis, and the x-axis is the line y equals 0. It will never touch it. So the line is called y equals 0. That's the name for the line. The reason it's the name for the line is this line right here, this x-axis line. No, that's why it's an asymptote. The reason it's called y equals 0 is because that's the value of y everywhere on this x-axis. Even if you go to negative 100, on the axis, y is still 0, because it doesn't go up or down. If you're on the axis, y is 0. So we call the x-axis y equals 0, because everywhere on the x-axis, y is always 0. So we just say y equals 0. It's kind of like calling the line y is always 0. Yes. All right. Now we're going to talk about a virus. Remember computer viruses? I mean, they're still around, but like they're not as like prevalent as they used to be. I feel like we have good like firewalls these days. Why is there so much giggling and talking? It's rude. All right. Okay. Somebody want to read this? Jocelyn?
A network administrator uses a function f(x)
equals 5x to model the number
5 to the x power.
to x power, model the number of computers the virus spreads to after x hours. If there are 1,000 computers on the network, about how many hours will it take for the virus to spread to the entire network?
Very good. Now, if you're like me, when you read a word problem like that, you're like,
No.
you pull a Brianna, you're like, that doesn't make any sense. And I want to go away and eat some ice cream. That's what I want to
Me
do.
too. Take me
Okay? I want to eat ice cream and forget that ever happened. But then I have to, face reality and go, okay, word problems are a part of life, and we need to break them down.
I want
We
to
need
go back
to.
to whoever created math, and then I want to and then I want to go back to
Okay.
okay.
If we don't have math, then we don't have money. So,
That's
better.
can we keep going?
Yes.
Thank you. So a network administrator, that's just a fancy word for the IT guy, right? So like Mr. Snitko, right? Mr. Snitko. Oh, Mr. Snitko, the one who's like always fixing all the computers and things. Okay, so I guess he has two jobs, fixing computers and yelling at Charlotte. So Mr. Snitko uses this function, f of x equals 5 to the x power, so similar to the function that we were just talking about, except the base here is no longer 2, it's 5. And that means our constant ratio is 5. Very good. Sit. Okay. So a very simple function right here. And this is the function that models. No, you did not. It's okay. This is the function that models the way that the virus is spreading. Do you have to go to the bathroom now?
Can I get your water?
Yes. You're welcome. Can everybody else stay seated for the next 15 minutes? That would be great. Thank you. So, this virus, look at he's got like a crazy face on. Can you guys see that?
No.
Yeah, it's like a virus emoji. It's a virus emoji. Okay.
Yeah, I kind of see it.
So the virus is like, it's got this like stopwatch, okay? Because it says the model the number of computers a virus spreads to after X hours. So a virus is like time me, see how I do. And then like his virus coach, he's like, all right, here we go, let's see how you do. And he hits the stopwatch and he goes, go. And he jumps into a computer. He's like, I'm in, coach, I'm in. Charlotte's like, I will not laugh. This is not funny. I don't like math. That's okay. He's like, I refuse to laugh at this ridiculousness. I get it.
Giggle.
So,
Giggle for it.
the virus, boom, the stopwatch starts and he's in one computer, infected. And the virus is like, I don't just jump from one computer to the next computer, to the next computer, and the computer after that. I multiply. I'm gonna go to 5 computers at a time. And when I multiply over here, then I'm gonna go to 5 computers, and that guy's gonna go to 5 computers. And then when we go to those computers, we're gonna multiply again. We're gonna multiply again. We're gonna multiply again, because it's multiplicative. Right? That's why an exponential is multiplicative, because it multiplies. That's how COVID happened too, right?
Yeah.
So we're not just talking about computer viruses, that's how actual viruses spread exponentially, right? Okay, so this guy's like, boom, I'm in. He spreads to, after 1 hour, wow, it takes him a whole hour to spread to 5 computers, it's pretty sad. Okay, so after 1 hour, he spreads to 5 computers.
How many firewalls and passwords do you
You
have?
just guys volunteer.
After the second hour, each of those 5 viruses spread to 5 other computers. Do you see how one little virus is spreading like crazy just after 2 hours? Look what happens after just 5 hours. How many computers? it spreads to?
3,125.
Very good. So let's analyze what's happening here. What does X represent?
The number of hours.
The number of hours. Very good. What does Y, or our output, represent? How many computers are infected? Very good. So X is the hours, and y, or our output, is the computers.
Bless you.
Thank you.
Go.
Now let's go back to our word problem, boys. He says it says if there are 1,000 computers on the network. So what are we looking for here?
Computers.
Dude.
Our y value. Is that you, Jocelyn?
Yes, it
Good
was.
girl.
I never looked
She's
Wow, she did not want you to get that dog in. What?
We don't know how many hours it took.
Exactly. That's
So
what.
aren't we solving for x?
Yes.
Okay, so take out the whole table.
Good job,
No, I didn't.
Oh.
I was-
Eat the table.
I was breaking down the question. You don't like those?
I'll take it.
Oh, okay. I
said
was
it's
not
okay.
trying to solve. I wasn't trying to solve it. I was just breaking down the question because it says 1,000 computers. I want us to think of, well, what are computers? That's our why.
What are you?
So we're gonna. What's a computer?
Computer.
So if we're looking for the computers, we are looking at our y values, which is also known as the output values, which is listed right here in our table, which they gave us. Yeah.
If the x is called domain, what's the y?
If the x is called what?
Domain, what is the y?
Range. So we see that 1,000 isn't in our table. So where would it be?
I don't know.
I
In
do
the air.
wonder.
Do you
I know.
what?
It would be in between 4 and 5.
Very good. Well, I was just looking for in between these two numbers because 1,000, if you're gonna see where it falls in this function table, it's gonna fall somewhere over here, right? So that means it's gonna fall the number of hours that pass, which is what they want to know. About how many hours will it take for the virus to spread to the entire network? It'll take somewhere between 4 and 5 hours,
4.5 hours.
which is a pretty good guess right there. But if you actually graph it, you can see a little bit more clearly. Now, when it's graphed, they've made the x-axis the number of hours because that was our input, right? The y-axis is the number of computers. They counted by 200s, but each little unit there represents 100 computers, 200 computers, all the way to 1,000 computers, because we want to see this function. All they did was the points on this graph. All that is these points: 0, 1, 1, 5, 2, 25. Look, 0, 1, right here. It looks like it's 0, 0, right? It looks like it's 0, 0, right?
Which is very, very tiny.
Yes, it's very, very tiny. But it's actually 0, 1. We can see that from our function table here. Then we have 1, 5, which again looks really tiny, right?
Yeah.
And then what's our next point?
1,
We'll go back to the
5.
table.
1, 5.
225.
225.
Oh, yeah.
What?
Wait, 220.
No, 25. You just did 5.
225.
Oh, yeah.
Yeah, we did 0, 1, then 1, 5.
You're saying like 225.
Oh, it does sound like 225. 2, comma, 25. I just said that. So we see that point here. And we see this one little virus right here, thinking it's big and tough, just infecting one computer at the start. It's only one computer.
Nope.
But it's not, because he multiplies exponentially. So even though it looks like he's starting kind of slow, the more computers he infects, the faster he grows. So he gets faster and faster and faster, shooting up all the way up here. So after 4 hours, he's at, what was it on the table here?
625.
625, right here. And then we have the value for after 5 hours, which was way over 1,000. But since we're looking for the 1,000th computer, how many hours, Binks? Gotta wake up, hon. the 1000th computer, we have to consult the graph because we see that our like little bendy exponential function here is shooting up so high. If we go to our y-axis and see at 1,000 computers,
It's like 4 hours, 15 minutes.
yeah, it's 4 something. Now,
That's a little wavy.
somewhere between 4 and 5. Closer to 4 or closer to 5?
Closer to 4.
Closer to 4. Okay, so the book estimates it about 4.3. You know how we can check that? Gotta stay awake? Gotta stay awake? You know how we can check that?
Is it like?
With a calculator!
Is it like?
Oh my God.
Get out your calculators.
4 hours and 18 minutes.
So how, now listen. If we're saying 4.3 hours, what are the hours? Our x or our y?
X.
Our x. So our function is f of x equals 5 to the x power. What do we plug in for x? 4.3. That's the exponent. So let's get out the calculators. You guys remember how to use your y to the x button?
I don't have a calculator.
You don't have a calculator? Here, take one of mine. I've got a bunch up here. Anybody else need a calculator?
It's 4 minutes, not a calculator.
It's not right.
You're right, it's not exact. It's not exact. Okay, check this out. Check this out. What do we type in first to find this?
5.
5. Then what do we hit?
The exponent button.
Y to the x power. Very good. The exponent button is right underneath the off button.
And then you type
Click that.
4.3.
4.3. Very good.
And it's 1012.910.
Yes. Now, is that pretty close to 1,000?
Yeah.
Yeah. So I'm going to say that's a good answer. But if you're like a little OCD about it, you're like, is there a closer answer? We could try something else. What should we try?
4.2.
Who said that? Very good. Why did you say 4.4?
Because that would make it cool.
Exactly. Very good. That would have made it go higher. Since we're trying to get down to 1,000, let's type in 4.2 as our exponent just to check it out. Let's try 5 to the 4.2 and see what we get. So base 5, oh, you're already doing it. Okay, base 5 times to the 4.2 power. Oh, wow. Whoa.
That's a bigger number.
No, went way down. Went way down. 862. So we got way far away from 1,000. So
4.25.
what?
4.25.
4.25. I love it. Okay, let's try 4.25. 5 to the 4.25 power. I think we could probably do this all day.
Oh, I know.
There's a jolly
5
It's
to
5 to the
the 4.25 power equals. Okay, we're getting higher. We're not close to
5 to
934.
4.275.
5 to the 4.275. 972.9.
Oh, 5 to the point 256.
0.28.
8.
You're just making it more.
4.58.
What'd you get? What'd you use?
It's only 4 times 5.
Wait, I got it.
Power 4.2.
I got so
4.29? 4.29, let me see.
Look, I got 4.29.
You did!
Oh.
You got so close. What did you use?
4.
He got 999.9.
What?
5 to the 4.92. I think.
You forgot. 5 to the 4.2.
4.92. I think.
4.
Oh wait, no,
no,
4.2.
No, probably 4.292.
I think.
Oh my gosh.
4.293.
Yeah.
4.29.
You should be an IT guy. 5 to the 4.292.
That's legendary.
No.
So close. 999.95224.
What did it
4.291.
Wait, what is
Should we keep going? No, we
4.2.
shouldn't. We need to move on.
4.29.
4.2.
But it is pretty impressive that you guys. What did you just get? It's not exactly 1,000, it's 1,000.4. It's actually further away than his. But guys, do you realize that you're getting more accurate answers than the book's answer? That's really good. We got even closer. We should all go into IT work. We would kill all the viruses
No, I probably make it work.
and stop them in their tracks. Okay, we have to move on.
I got so close.
Okay, this is really, really important. Copy this down. We have already talked about these definitions, but I want you to write down this model here, because this is what you're going to carry with you to your homework, your quizzes, your tests, and we're writing this model right here. What this is your model for the exponential function. The good news is you don't have to memorize it. It's on your EOC reference sheet, which is available to you on Canvas always. It's at the very top of your course page. You can use that on any homework, quiz, test, and your EOC. But you have to know what it means in order to be able to use it properly. This is our exponential function. It is the what? Product, which means
Like
The answer after multiplication.
multiplication. Very good. The answer of a multiplication problem. So it is the product multiplying of an initial amount. What does initial mean?
The beginning.
Beginning or starting, right? The initial amount. So initial amount is here represented by A. We can think of that as A as the initial letter of the alphabet. Stay awake, okay? And the initial or starting letter of the alphabet. So A, initial amount. And a constant ratio. We talked a lot about constant ratios already. That is our constant ratio, which is represented by B. And if you need help thinking of that, B also stands for base, the base of the exponent. So the function is the initial amount times the base, or the constant ratio, to the exponent x. Now, the two functions we've worked with so far today, I'm going to write them on the board. First, we worked with function of x equals 2 to the x power. We also worked with function of x equals 5 to the x power. That doesn't look the same as this. Can anybody tell me why? What's missing? Grayson?
Times BX. Or
No.
A.
Yes, that's what's missing from these. Now, was it missing or was it just
Invisible.
That was hidden.
It was hidden, it was invisible. Why was it hidden? Why would you ever hide a number? Because the initial value was 1. And we can go back to our table of values and see that. The initial value when that virus, remember when the virus coach was like, go! And he starts a stopwatch and hasn't hit, 1 hour hasn't passed yet. He just said, he hits one computer. That was the starting value, 1. And then this one that didn't have a fun little story or a picture, this graph of 2 to the x power, we could see on our table that when x was 0, when it started, the y value was 1. So that was, now we are going to, on Monday, we're going to talk about interest and investments, where the starting value is not going to be 1 anymore. When you're opening an account or investing in something, your starting value might invest $5,000 in a company one day. Maybe not now, but one day. So that will be your initial investment. All right, let me just see. So real quick, before we go, and just a reminder, your homework is due on Tuesday, not Monday. Before we go, I still have a minute and a half, so don't move. No, don't pack up. If we are given a function table, but we're not given the function in written form, we can write it ourselves, because if we know the standard way to write a function, we simply use the table to fill in the information. And this will also be in the homework help video if you want a further example of this, okay? So, another thing about this table is it doesn't give us the starting value, so we can actually find that 2 ways. But remember our B, our base, is the constant ratio. How do we find the constant ratio?
By trying to find what it's multiplying.
Yes, finding what the y value is multiplied by to get to the next y value. Now, if the numbers get a little more complicated, how can you solve that? You divide. Very good. So you take the further y value divide it by the y value before that, and that will give you the number that it was multiplied by, right? You just go backwards. So we can see here that 36 divided by 12 is 3, 108 divided by 36 is 3, so we see our constant ratio, which we can automatically fill in right here. I'm gonna let you go in 10 seconds, okay? We fill it in right here. Then, we don't know our x and we don't know our a, our initial amount, so we can use one of the coordinate pairs, pick the easiest one you can find, plug it in, and solve for a. We can, you guys gotta go. Sorry.